Hello, everyone. My name is Zaneta. I'm from University of Leeds Storm Lab, and I'm going to talk to you about mechanical reinforcement towards fully soft magnetic endonasal manipulators. So let's start from general soft robots. I know we talked about it a little bit today, but just a small recap. So the main advantages of soft robots in general are delicate tissue interaction with a delicate interaction with the environment, and they are compliant, and they are also cheap to manufacture. And there are different actuation systems that we can use to move our soft robots. And the most popular one is pneumatic control, where through supplying air pressure to pre-designed channels or chambers in the robot, we control its movement. This works well at certain scales and for a relatively small number of degrees of freedom. But if we would like to add multiple degrees of freedom to this kind of design, we would have to add more channels and more chambers, which then becomes quite challenging to miniaturize and in general handle it at the smaller scale. Because as we can see, the backstage of this sort of control system on the left-hand side contains a lot of components. So that's also another reason why it's difficult to miniaturize. So another actuation method is through magnetics. In this case, we apply external magnetic field to the soft robot that is either filled with magnetic particles or consists some permanent magnets inside. And that external field then creates torques and in consequence moves the robot. So in this case of actuation, the miniaturization is much easier since the material of the robot itself works as our actuation system. So the actuation is on board already. So there's no need for any wiring, there's no need for any connections. And the only external equipment that we need is the way of applying magnetic field. So in our lab, we mostly work with soft magnetic robots that are actuated by permanent magnets. But other popular way is using electromagnetic coils as well. So one of the bigger research topics in magnetics are continuum soft robots. So today I'm going to focus on these type of devices for medical applications. So the first type, the one that is mostly seen in literature, is robots that are tip magnetized or axially magnetized. So these devices provide with good navigation. However, because we don't have control over the whole length of the body, because of its simple magnetization profile, it might deform our anatomy because only tip of the robot is being sort of dragged along the lumen with magnetic torques or forces. So while navigating, it can touch walls of the anatomical pathways and deform them. So the second type of magnetic continuum robots are the ones with optimized magnetic profile. So the robot is divided into magnetic segments, and each of the segment is magnetized in a different direction. And these directions are based on optimization. So before we fabricate the robot, we analyze the path that we are planning to navigate, and we optimize the magnetic profile so that after applying certain external magnetic field, our device will form into the shape of the lumen that we are navigating through. And this is meant to minimize tissue interaction and provide more smooth navigation. So even though these two approaches work well and they have both different advantages, in both of them we can observe some instability. So here we can see on the video to robots that are in their unstable scenarios. So this happens in cases where magnetization direction of the robot and the applied field direction are orthogonal to each other. So in that case, instead of creating desired deflection, our robot twists about its main axis. And this can cause some unpredictable behaviors, of course, in our control. So to improve that, to improve the control, we should minimize that, that twist about the main axis. So to overcome this twisting behavior, we have developed fiber reinforced manipulators, where a double helix structure is encapsulated in the silicone. And we saw that this method worked very well. We achieved 67% reduction in torsion. However, since in our lab we are mostly focused on medical applications, we always aim to miniaturize our devices. And we found that with this method, it would be quite challenging to manufacture at smaller scale. And that is because the fibers were manually fabricated, and then they were manually aligned and then encapsulated together with magnets in the silicone. So while we improved this method to try to miniaturize these manipulators with fibers, we developed different methods for restraining torsion in magnetic soft robots. So another design is sort of monolithic solution where we have a soft core with also soft double helix structure that is wrapped around the core. And thanks to this design, we can achieve variability and stiffness between different axes of the manipulator, so that it can deflect only in one plane. And because of that, it also increases its torsional stiffness. So for this design, we used 3D printed molds with silicone Dragon Skin 30 and hard magnetic particles with 1-to-1 ratio, so that the whole manipulator can be fabricated in one step, so that it's also easy to miniaturize. So in this initial study, we developed 2 different designs, varying the helix thickness and number of revolutions of the helix as well. So to find the better design of the 2 presented, we have compared it to a cylinder. Not sure what the videos are playing. Right, so we compared it to a cylinder and we collected data on pose of the robot from the optical tracking system while we were applying different fields in the magnetic workspace. And to find the most optimal design from the 3, so from 2 designs we presented and from a cylinder, we looked at the bending to torsion ratio. And this is because in this case, the optimal design would restrict torsion, but it would still allow for high deflections. So we found that the thicker helix worked better, and we chose that one to continue further testing. Yeah. So due to the variability of stiffness between different planes and this design, we can configure different segments on top of each other in the way that we get variable stiffness along its length. So then by magnetizing these 2 segments in specific directions, we can independently control them with different magnetic fields. So this gives us improved maneuverability, which can be beneficial in applications where high deflection is needed. And with this configuration, we can deflect the top and the bottom segment in different axes. Yes, so we think that a potential application for these manipulators could be endonasal surgery, and this approach in general is used to treat tumors of pituitary gland. And currently, one of the biggest challenges in these procedures is the rigidity of the toes and the fact that they use multiple toes at once in a very small workspace. So for example, a camera in this procedure is also mounted on a rigid scope. And so the visibility of the operating site is quite poor. So this can lead to situations where not a whole tumor is removed during the surgery and another surgery is needed. So we hope that this research can contribute to developing improved endonasal toes that are flexible, smaller, and safer to use to improve the outcome of these kind of surgeries. So what I presented today are only some initial results and kind of proof of concept, but future work will involve some structure optimization study with CONSOL, and we will also explore adding functionality to our robots, such as camera and other surgical tools, to test them in anatomical phantoms. Thank you to the team. And if you are interested in our magnetic platform and want to learn a little bit more about what we do, my colleague Michael is presenting tomorrow at 3:15 British time. So please join us tomorrow as well. And thank you.